For capacitor, we have seen that the charge is equal to the capacitance into the potential difference across the plates of the capacitor. And for a parallel plate capacitor, we had this relationship C equal to epsilon 0 A by D, and for a isolated spherical conductor of radius R, the capacitance was 4 pi epsilon 0 R. Today we shall derive the relationships for capacitance of a spherical capacitor and a cylindrical capacitor. But before that, let us look at the SI unit of capacitance. SI unit of capacitance, C equal to Q by V, will be obviously, for Q it is coulomb, for V it is volt. So the SI unit of capacitance will be coulomb per volt. This coulomb per volt has a special name. It is called as farad and is denoted by capital F. So the SI unit of capacitance is farad. Charge per unit potential difference, or coulomb per volt, popularly called as farad. But convenient units are microfarad, which is 10 to the power minus 6 farad, or picofarad, which is 10 to the power minus 12 farad. Now we shall discuss the capacitance of a spherical capacitor. A spherical capacitor will consist of two concentric spheres. The inner is a solid sphere and the outer is a spherical shell. The inner one is a solid sphere of radius, say A, and the outer one is a spherical shell of radius, say V. We assume that charge Q is deposited on the spherical capacitor, which means that plus Q is deposited on the surface of the inner sphere, plus Q is deposited on the surface of the inner sphere, and minus Q is deposited on the inner surface of the outer spherical shell. On the inner surface of the outer spherical shell. Now, in order to calculate the capacitance of this spherical capacitor, we have to first calculate the potential difference that will exist between the plates. I have assumed that the inner sphere is positively charged and the outer spherical shell is negatively charged, but the same amount of charge Q appears on both. So definitely a potential difference will exist with the inner sphere is at the higher potential and the outer spherical shell is at the lower potential. Let me name the inner sphere as sphere N and the outer spherical shell as M. So the potential difference that exists is Vn minus Vm, which is equal to V, say. The inner sphere is the sphere N and this is the spherical shell which has been named as M. Now, in order to calculate the electric field between the sphere and the spherical shell, or electric field in the region between the plates. Remember that plates does not mean rectangular or spherical in shape. Plates means of any cross section of any nature, there must be a separation between them. So in order to calculate the electric field, we will assume a Gaussian surface, and the Gaussian surface will be a sphere by symmetrical charge distribution, because this is a spherically symmetric charge distribution, so the Gauss surface will be also a sphere. In order to calculate the electric field in the region between these plates, we consider a point P and a Gaussian surface, which is obviously a sphere, will pass through this point P. This Gaussian surface is assumed to have a radius r with respect to the center O, because all the spheres are concentric. So let me assume that this Gaussian surface has a radius r. This dotted sphere is the Gaussian surface, which is in the shape of a concentric sphere of radius r. To be precise, it is concentric spherical shell of radius r. So what we are trying to do is, we are trying to calculate the potential difference as negative of the line integral, that is Vn minus Vm, which has been written as V, is equal to negative of the line integral of E vector between M and N. Now, with respect to this charge distribution, it is quite obvious that electric field lines will propagate from the inner sphere and it will move in radial direction, because electric field lines are always perpendicular to the surface of a conductor, and so electrical field lines, because the inner sphere is positively charged, the electrical field lines will emerge out of that sphere, and because the outer spherical shell is negatively charged, the electrical field lines will terminate into that spherical shell. So the electrical field lines are radially upward. So therefore, we have to calculate this. First, we have to calculate E vector in terms of Gauss law, and then we have to perform this integration. So let us do so. So the Gaussian surface has a radius r, which is obviously less than the outer radius b and greater than the inner radius a. We know that E vector dot ds vector executed over the closed Gaussian surface, let me call that as S, is equal to 1 by epsilon 0 times of the charge enclosed. If you go through the diagram again, you will realize that the charge enclosed is Q, because the Gaussian surface encloses the inner sphere whose charge is Q. And E vector, because it is in the radially outward direction, so any small elemental area will also be along the radially outward direction. So if you say that E vector is ER hat, then ds vector is also ds r hat. Because E vector is uniform, what you get is E vector goes out of the integration, and this is the surface integral over the Gaussian surfaces. The Gaussian surface is of radius r, so its surface area will be 4 pi r square q by epsilon 0. So the electric field in the region between the plates is 1 by 4 pi epsilon 0 q by r square. Q by r square. Now we have to perform the potential difference, as we have already said. It will be V equal to integration of E vector dot dl vector. Now in this case, dl vector is along the path connecting the spheres, which is obviously along the radial direction. So you can just write this as E dr, and it will be integrated from A to B. Again, E is uniform, so this is, E should be written as 1 by 4 pi epsilon 0 q by r square dr. So q by 4 pi epsilon 0 goes out of the integration, it becomes dr by r square integrated from A to B. The integral of dr by r square is r to the power minus 2 plus 1 by minus 2 plus 1, that is minus 1 by r. So this gives minus q by 4 pi epsilon 0 1 by r limits b and a. So therefore v becomes q by 4 pi epsilon 0. I am changing the negative sign by changing the limits here. So it becomes 1 by r b to a. So this becomes q by 4 pi epsilon 0 1 by a minus 1 by b, which is q by 4 pi epsilon 0 b minus a by ab. So this is the potential difference between the plates of the capacitor. Now we know that the capacitance is charge per unit potential difference. So this becomes q divided by q upon 4 pi epsilon 0 b minus a by ab. So q will cancel out and this term will go on the numerator. So what we have is 4 pi epsilon 0 AB divided by B minus A. 4 pi epsilon 0 AB divided by B minus A. This is the capacitance of a spherical capacitor. Next, we shall derive or obtain a relationship for the capacitance of a cylindrical capacitor. Similar to the discussion of a spherical capacitor, a cylindrical capacitor will also consist of a solid inner cylinder, and a coaxial outer cylindrical shell. So with respect to the same axis, we will have a coaxial cylindrical shell. The inner cylinder is of radius A and the outer cylinder is of radius B. Suppose positive charge is deposited on the surface of the inner cylinder. Because it is solid, charge will distribute itself uniformly over the surface, and a negative charge will deposit on the inner surface of the outer cylindrical shell of radius B. So again, let me call this inner cylinder as M and the outer cylinder as M. So we have to calculate the potential difference between the plates, that is Vn minus Vm, which we shall call as V, and that will again be the negative of the line integral of E vector from M to N. In order to calculate E vector, we have to use Gauss theorem, and for that we have to consider a Gaussian surface in the shape of a cylindrical shell. Now the Gaussian surface is obviously a cylindrical shell because this represents a cylindrical symmetry situation of charge distribution. So the Gaussian surface will be a cylindrical shell of radius r such that r will be less than b but greater than a. So we have to calculate E vector in the region between the plates, in the region between the inner solid cylinder and the outer cylindrical shell. So let us consider some point P whose distance from the axis is r, when r is less than b but greater than a, and we have to assume a Gaussian surface in the shape of a cylinder that passes through this point P and is coaxial with both the cylinders. Now this Gaussian surface is of radius r. This is the Gaussian surface. So in order to apply Gauss law, we know that E vector dot ds vector over the closed Gaussian surface in the shape of a cylinder is 1 by epsilon 0 of the charge enclosed. Now this Gaussian surface, which is the dotted surface as shown in the figure, will enclose only the charge that lies on the surface of the inner cylinder, that is plus q. So this is suppose plus q and the outer has charge minus q. So obviously this q enclosed will become plus q or simply q. Because E vector is along the radial direction and ds vector is also along the radial direction, E vector is uniform too, so this becomes 1 by epsilon 0 times of the charge enclosed, that is q. The integration of ds over the surface S, that is the Gaussian surface, will produce the lateral surface area of the cylinder, which is 2 pi rl. If I assume that the cylinder is of length L, then this produces E into 2 pi rl is 1 by epsilon 0 of the charge enclosed, which gives E equal to q by 2 pi epsilon 0 1 by rl. Q by 2 pi epsilon 0 1 by rl. So now from this we have to calculate the potential difference, and from the potential difference we will get the capacitance. So therefore V will become E vector dot dl vector with respect to limits a and b, the respective radius of the inner cylinder and the outer cylindrical shell. E vector and dl vector in the same direction, so because the dl vector will represent integration along the path connecting the inner cylindrical inner cylindrical surface with the outer cylindrical shell. So E vector and dl vector in the same direction, so this we get as E dl in the sense from A to B. Now dl and dr are in the same direction, so this dl can be represented by dr and E will be replaced by this. So E dot dl will be integrated. Now E dot dl will produce E dot dr, because dl is nothing but it is a small segment along the path connecting the inner cylindrical sphere to the outer cylindrical shell. So dl vector can be replaced by dr vector, and both dl vector and dr vector in the same direction. Also E vector is along dr vector, so we can just write it as E dr, integrate from A to B. Taking the value of E from here, what we get is V equal to, instead of E we will write q by 2 pi epsilon 0 1 by rl, but apart from r everything else is a constant. So q by 2 pi epsilon 0 L will go out of the integration and dr by r will remain in the integration. The integral of dr by r is ln r. So this is q by 2 pi epsilon 0 L ln r integrated from a to b. So this will give q by 2 pi epsilon 0 L ln b minus ln a. Log b minus log a is log of b by a. So what we get is v equal to q by 2 pi epsilon 0 capital L, which is the length of the cylinder, ln b by a. Now the capacitance is equal to charge per unit potential difference. So q by v, when we will do q by v, this q will cancel out. So therefore we get C as 1 by 1 upon 2 pi epsilon 0 L ln b by a. Because the q and this q will cancel out. Let me again write still q by v, where v is this one. So q cancels out. So this implies C equal to 2 pi epsilon 0 L will go in the numerator ln b by a. This is the expression for the capacitance of a cylindrical capacitor. In the last expression for the capacitance of a cylindrical capacitor, I wrote 2 pi epsilon 0 L ln b by a. By mistake, I did not write the division symbol. So actual expression is C equal to 2 pi epsilon 0 L divided by ln b by a. Now from this expression, it is also that the capacitance again depends upon the geometrical factors, that is the length of the cylindrical capacitor, the radius A of the inner solid cylinder and the radius B of the outer spherical shell. Energy stored by a charged capacitor. Suppose initially the plates of a capacitor has stored charge Q on it. Let initially charge Q is deposited on the capacitor plates. And so a potential difference will exist between the plates. Now in order to deposit some more amount of charge on the plates, we have to do work against that potential difference. So in order to deposit charge dq on the plates, work done, very small amount of work done is dW, which is equal to the potential difference between the plates when charge q was present on them, that is V, into the additional charge that we are trying to deposit, that is V dq. And this work will be stored as potential energy. Now we know that the potential difference can be expressed as Q upon C. Since Q equal to C into V, so V is obviously Q by C. So therefore, this dW can be written as Q by C dQ. In order to deposit charge, charge Q. This is a finite amount of charge that we are trying to deposit from a previously uncharged condition. That means we are assuming that initially the charge was 0 and after some time Q amount of charge has permanently deposited on the plates of the capacitor. So in order to deposit charge Q from a previously uncharged condition, the work done is W equal to integration of dW from the value of small q as 0 to small q as capital Q. This is equal to, we will replace q dq by c, where c is a constant, so it will go out of the integration, q dq from 0 to capital Q. Integration of q dq is q square by 2, so q square limits 0 to capital Q. So this will give you q square minus 0 square by 2. So the work done will be capital Q square. Sorry, I forgot to write C here. It is 2C, 1 upon 2C. So this is Q square by 2 into capacitance C. This work will be stored as potential energy of the plates and it will be denoted by capital U. This work is stored as potential energy, electrostatic potential energy to be precise, potential energy of the charged capacitor. Which is generally denoted by capital U. So therefore, that U will be Q square by 2 into C. Now we can express this Q square by 2C in different forms. We know that Q equal to C into V. So Q square becomes C square V square by 2C. So U also takes this form where C cancels out and becomes half CV square. The potential energy is equal to half into capacitance into square of the potential difference between the plates. This is also a popular expression that we denied. Like we could have written in terms of V also. Now from Q equal to CV, I can write V equal to Q by C. So if I try to replace C, I can write C equal to Q by V. So therefore this U will become Q square by twice of, instead of C is Q by V. So what we get is a Q cancels out and this V goes to the numerator. So half into Q into V. Another expression for the potential energy is half into V. So either this one is used or this one or this one. Now we will discuss capacitors in series. Let us assume that there are three capacitors which are in series. Let the capacitance of the capacitors be C1, C2 and C3 respectively. Let this combination be connected to a battery and suppose the battery is of EMF epsilon. The capacitors will get charged, but because they are in series, potential difference at the ends of each capacitor will be different, but the same charge will deposit on them. So let charge Q deposits on the plates of the capacitor, plus Q minus Q, plus Q minus Q, plus Q and minus Q. And the potential difference across the ends of the first capacitor is suppose V1. At the ends of the second capacitor it is V2, and at the ends of the third capacitor it is V3. As we know that Q equal to C into V, so we can write Q equal to C1 V1 for the first capacitor, Q equal to C2 V2 for the second capacitor, and Q equal to C3 V3 for the third capacitor, which means that V1 is Q by C1, V2 is Q by C2, and V3 is Q by C3. Now, if we replace this combination of three capacitors by a single capacitor such that the same battery is connected to the ends of that capacitor. So, this equivalent diagram will be something like this. The three capacitors are replaced by a single capacitor and the same battery is connected to its ends. Let the capacitance be C. So this C will be called as the equivalent capacitance of the combination of these three. So therefore, with respect to the same battery, it will deliver the same amount of charge, plus Q on one plate and minus Q on one plate. Now for this capacitor, the potential difference developed at the ends of it will be obviously E, which will be equal to Q divided by C. And as the 3 has been replaced by a single one, the potential difference at the ends of the individual capacitance, they will add up to produce E again. So now E is equal to V1 plus V2 plus V3. So we replace and substitute for V1, V2 and V3 as Q by C1 plus Q by C2 plus Q by C3. Taking Q common from the right hand side and cancelling out, we get 1 by C is 1 by C1 plus 1 by C2 plus 1 by C3. So capital C is the equivalent capacitance of the series combination of C1, C2 and C3. So if there are n capacitors which are combined in series, the equivalent capacitance for n capacitors in series, the equivalent capacitance is 1 upon C equal to 1 upon C1 plus 1 upon C2 plus 1 upon C3 plus 1 upon C4 and so on. So that can be written as summation of 1 upon Ci, where I ranges from 1 to n. The next topic is capacitors in parallel. Now from this, if you compare with resistance in series, you are getting just the opposite formula. For resistances in parallel, we obtain 1 by R is 1 by R1 plus 1 by R2 plus 1 by R3. And for capacitors in series, we obtain 1 by C as 1 by C1 plus 1 by C2 plus 1 by C3. So if we consider parallel connection of capacitors, we will get the same formula as that of series connection of resistors. So let us consider capacitors in parallel. So let us again assume there are three capacitors which are connected in parallel to a battery. The capacitance are respectively C1, C2 and C3, and the battery is of EMF epsilon or E. Now, because these capacitors are connected in parallel, the same potential difference will occur at the ends of each capacitor, but different charge will get deposited. If this battery is capable of delivering a charge Q, then Q1 will deposit on the plates of the first capacitor, Q2 will deposit on the plates of the second capacitor, and Q3 will deposit on the plates of the third capacitor. But the potential difference at the ends of each capacitor remains same, and that is E. So now we can write Q1 as C1E, Q2 as C2E, and Q3 as C3E. So if we replace the combinations of these three capacitors by a single capacitor such that the same battery is connected across its ends, what we get is a single capacitor of capacitance C, and the same battery is connected at its ends. Now this battery, suppose, deposits charge Q on the capacitor, then this C will be called as the equivalent capacitance of the parallel combination of these three capacitances. So therefore from here we can write Q equal to CE. Because charge is conserved, Q is actually Q1 plus Q2 plus Q3. So CE is equal to C1E, C2E plus C3E. Taking E common from the right hand side, we cancel out from both sides E, and we get C equal to C1 plus C2 plus C3. So this will be the equivalent capacitance of three capacitors in series, in parallel. This is a similar expression that we obtained in the case of resistances in series. For resistance in series, the resistance value are added up to provide the equivalent resistance, and for capacitors in parallel, the capacitances add up to produce the equivalent capacitance. So if there are n capacitors in parallel, the equivalent capacitance will be C1 plus C2 plus C3 and so on up to Cn. So this can be written as summation of Ci, where I starts from 1 to n. Next, we shall discuss the loss of energy due to sharing of charges. Suppose we consider two conductors. The shape does not matter. It is not necessary that I have drawn a spherical shape, which means that the conductors will be spherical only. It can be any two type of conductors. Suppose initially the conductors have capacitance C1 and C2 respectively, and they are at potential V1 and V2 respectively. The charge deposited on these conductors be Q1 and Q2 respectively. So initially we can say for the first capacitor Q1 is C1 V1, and for the second capacitor we can say Q2 is C2 V2. The electrostatic energy that these conductors will store is say U1 equal to half C1 V1 square and U2 equal to half C2 V2 square. So therefore, the total electrostatic energy stored by the system is U initial Ui, which is U1 plus U2, and this Ui will be half C1 V1 square plus half C2 V2 square. Now suppose we connect both these conductors by a metallic wire. When we do so, charges begin to flow until both these conductors will achieve a common potential. Because they are conductors, if they are connected by a metallic wire, definitely charge will start to flow from one conductor to the other. Depends on what amount of charge is stored. If Q1 is greater than Q2, then definitely charge will start flowing from the first to the second. If Q2 is greater than Q1, charge will flow from the second to the first. So if we connect them by a conducting wire, charges will start to flow, and the flow of charges will continue until both these conductors will achieve a common potential. And when they achieve a common potential, the charges become Q1 dash and Q2 dash. So suppose they are connected by a conducting wire. So after connecting by a conducting wire, the charges that appear is suppose Q1 dash and Q2 dash, and they will acquire a common potential. Both will achieve a common potential, suppose V. So now the situation will become what we call as the final situation. The energy of the first one is suppose U1 dash, it will be half C1 V square. The second one will store electrostatic energy U2 dash as half C2 V square. Now by the conservation of charge, we can say that in the previous situation, before connecting with a conducting wire, the sum of charges was Q1 and Q2, and after connecting by a conducting wire until they achieve the common potential, the charge is now Q1 dash and Q2 dash. As charge is conserved, the sum of Q1 and Q2 must be equal to Q1 dash plus Q2 dash. So Q1 was C1 V1 and Q2 was C2 V2, and here Q1 dash is definitely C1 V and Q2 dash is definitely C2 V. So if you take V common, and we can now write C1 V1 plus C2 V2. Taking V common, we get C1 plus C2, which will come in the denominator. So that will be C1 plus C2. So this is the value of the common potential that both condensers or conductors will achieve. Now, if we can realize the energy stored by this system of two conductors, there will be some loss of energy, and that loss of energy will appear as heat that will flow through the connecting wire. This we can definitely show mathematically. So we have already written U1 dash and U2 dash. So after connecting by the conducting wire, the total energy of the system is say UF, or final energy is U1 dash plus U2 dash, which will equal to half C1 V square. Instead of V, we will write this, and U2 as C2 V square. So we can take half common, C1 and C2 V square, where V square will be, instead of V square we will write this one, C1 V1 plus C2 V2 by C1 plus C2 whole square. Now C1 plus C2 whole square in the denominator will cancel out with C1 plus C2 in the numerator, and we get half. After expanding this one, C1 square V1 square plus C2 square V2 square plus 2 C1 C2 V1 V2 divided by C1 plus C2. Now we will calculate the change in energy, or delta U, as Ui minus Uf. So remember that Ui was half C1 V1 square plus half C2 V2 square. From this we have to subtract Uf, which is this much, C1 square V1 square plus C2 square V2 square plus 2 C1 C2 V1 V2 divided by twice of C1 plus C2. Now let us simplify this one. So this implies delta U will be, taking the LCM. The LCM is obviously twice of C1 plus C2, and so C1 plus C2 will be multiplied with the numerator of this one. So what we get is C1 V1 square into C1, that is C1 square V1 square C2 V2 square with C2, so we will get C2 square V2 square C1 C2 V1 square plus C2 C1 V2 square, or C1 C2 V2 square, minus this term again, minus C1 square V1 square minus of C2 square V2 square minus of 2 C1 C2 V1 V2. This is the term in the numerator. So now you can see that C1 square V1 square will cancel out, C2 square V2 square will cancel out. So what we get is, and we can take C1 C2 as common. So if we write C1 C2 as common, we get V1 square plus V2 square minus 2 V1 V2. Divided by twice of C1 plus C2. Now V1 square plus V2 square minus 2 V1 V2 is V1 minus V2 square. So C1 C2 V1 minus V2 square divided by twice of C1 plus C2. This is indeed a positive quantity because C1 and C2 are definitely positive, and whatever be the values of V1 and V2, if you subtract and square it, this will definitely be a positive quantity. So because delta U was initial energy minus final energy, and that turns to be positive, the initial energy is definitely greater than the final energy, which means that there is a loss of energy due to sharing of charges, and that loss of energy will appear as heat flowing through the connecting wires. So this expression determines the final loss in energy. Because delta U is greater than 0, delta U was Ui minus Uf, which is greater than 0, which means Ui is greater than Uf.